power to which the highest order derivative is raised. Is the power to which the highest order derivative is raised. Is the power to which the highest order derivative is raised. Is that thinking? Yes. Okay. So what's the other one? Order, right? Okay. So I'm coming. Let me look at the order of a differential equation. The order of a differential equation is the highest differential coefficient. The order of a differential equation. The order of a differential equation is the highest differential coefficient. Is the highest differential coefficient present in the equation. Is the highest differential coefficient present in the equation. Is the highest differential coefficient present in the equation. You get it? Okay. So let's revisit this now. What will you say about this? What is the order? Order is 1. What is the degree? 2. No. The degree is going to be 1. This is the highest order derivative you have in the equation. What is its power? 1. Do you understand that? So it is the highest order derivative that determines the degree. Do you understand me? That means you can have other derivatives that are to greater powers. So far this is the highest and it's the power of 1. It's still degree of 1. Is that clear? Yes, sir. Okay, so let's look at the questions here. Look at the first one. So what are the things you want to answer? Is it ODE or PDE? The first one. PDE, right? Yes, sir. The first one. Look at it. We are talking about number 3. Partial differential equation. PDE means partial differential equation. Partial differential equation means it carries partial derivatives. Is that clear? Instead of ordinary derivatives. So, is this clear? So, look at number 3. You don't have the question. Okay, that is. You can share with him now. So, the first one is what? Partial differential equation. Is that clear? Yes, sir. What is its degree? What is its degree? Degree. No. Degree. Oh, degree 1. Degree 1. Degree is 1. Degree is the power of the highest order derivative. Do you get that? Yeah, degree is 1. Order is what? 2. Degree is 1. Order is 2. Is that clear?
How is order 2? Is it that 1 plus that?
Because it's not partial derivative. Alright, we have to go to Is it partial or ordinary? Ordinary. Alright. So, what is its order? Order is 1. What is its degree? 1. Is it linear? No. Because of course XY. Yes, it's non-linear. So let's move on. Number 3. That's number 3. Is it PDE or ODE? ODE. Okay. Is it? What is the order? 5. Order is 5. The degree is what? 1. Good. Okay. Is it linear? Yes. Is it homogeneous? Yes. Shall we move on?
How is it homogeneous?
Like,
it's equal to 3 1.
Why is it equal to 0? Why is it equal to 0?
When you have because you said you should not have any other you get it. Okay, just cos x or y cos x. But it's taking cos of xy. Cos of y. Now you read the definition again. So either have just y or its derivative standing in not as functions. I would together know that they are inside some other functions. That was why e raised to power y made that one non-linear. I remember why we said that one. Because of e raised to power y, that is some function of y. You cannot have e raised to y together. You cannot have power of y. Roman figure 4, are you there? Okay. OD, right? Okay. Order of 2, degree of 1. Is it linear? Yes. It is linear, but not homogeneous. It is linear, but not homogeneous. Is that clear?
Yes, sir.
Okay, the next one. Roman figure 5. Partial differential equation. Is it linear?
Only God can. Only God. Yes.
Is it linear?
Yes.
What is the dependent variable? U. You can see power of u here. You can see u squared, which makes it non-linear.
Yes.
Yes. Alright, so let's move on. No, it is when it is linear.
What of the
Okay, number 1. Number 1, is it linear? Yes.
So which is that?
Roman figure 1, the same number 3.
Okay.
Is it linear? Yes. What's the dependent variable? U. Do you have any power of u or its derivative here? No. Do you have any function of u or its derivative? No. So Roman figure 1, number 3, Roman figure 1, the partial derivative. It is linear,
Yes, sir.
but not homogeneous because of the sign X.
what is this?
Can we move on? Can we move on now? Number 4. Number 4, can we move on? Can we move on?
Voila.
Okay. Number 4. What is the degree of the following differential equations? Pay attention now, pay attention. Number 4. Remember figure 1. What is the degree of the following differential equations? Remember figure 1. What is it? 1. Okay. Remember figure 2. 3. Remember figure 3. 4. 5. 4. Look at the highest order derivative. Do you understand that? The power of the highest order derivative. Do you understand that? Is what determines the degree. So it is 4, yes. Because the highest order derivative is the square y is x squared. So its power is what determines the derivative. Do you get it? Okay. So now let's talk about solution of differential equations. So what we solve some differential equations? The highest order derivative is the y dx, so its power. That's the degree. Can we move on now? Alright. So look at this now. So number 5 has to do with, listen please, listen. Yes sir. So pay attention now, just look at the board, look at the board. Can we move on? Look at the board now. Whenever you are given differential equations, you first need to identify what kind of differential equation it is. So it's your ability to identify that will actually help you solve the problem. Because different kinds of differential equations will have different solution approaches. So depending on the form, you will have a particular way to solve the differential equation. So what's really important is that you are able to identify the kind of differential equation you have been given, so you know the kind of solution that is applicable to it. Okay, so let's deal with this first part. We're talking of variable separable differential equation. That means that you may have a differential equation where you can easily separate the variables. This is what we mean by that. Look at something like this for a very simple situation. You can have, I made an example the other time of having y equal to x squared and the y dx being equal to 2x. Have you? From here I can easily say that the y is equal to 2x dx, or if you like, the y minus 2x dx is equal to 0. Or if you like, I can say x dy minus 2x squared dx is equal to 0. All together. Alright, so in this case, listen now. What we are saying is this, because you have the y here, you have the x here, and listen, you can easily separate the variables. It means that you can easily return to something of this nature and actually integrate directly. And so because of that, we say that the variables are separable. So this is what we mean. So at the end of the day, you can have something like this. Dy, okay, x dy is equal to 2x squared dx. Then you can separate them out. What do you mean by that? You can have it such that dy will only have as its coefficient those expressions or terms carrying y. All together, and the x we only have as its coefficient those expressions carrying x. So that way I can say that this is simply the y is equal to 2x squared over x dx. Is that clear? So this way I can integrate both sides. Is it clear?
Yes, sir.
So I can say that integral of the y should be y, and integral of this is just 2x, Abby. It should be x squared plus c. Is that clear? Constant of integration. Does it make sense to you? Then I will say this is the solution of this differential equation. The differential equation could have been given this way or this way. Is that clear? Okay, so it's quite easy when you have a variable separable differential equation. So these are examples of those. So let's take them one after the other so you see what we are talking about. I'm going to solve some of them for you, then you solve the others.
So these directly.
at the first one. You are given y prime is equal to 3x squared y. So are the variables separable?
Yes, sir.
So you can say that this is the y, the x equal to 3x squared y. It's obvious that you can separate out the variables. Does it make sense to you? You can have those carrying only x separated from those carrying only y. Does it make sense? Okay, so at the end of the day, when I cross multiply this, I'm going to have the y equal to 3x squared x. 3x squared y, happy?
Yes.
Then I can bring the y to this side. That will be 1 over y dy equal to 3x squared x. So I've separated the variables. That's there. And then we can integrate both sides. Is it clear? So what's the integral of 1 over y?
Lane y.
That's lane y equal to the integral of this. That's x cubed, happy? Then plus some constant. So you know that in my solution I want to make y the subject. To make y the subject, just recognize that this is log this to base e, right? So you can raise this to power of e. Is that clear? Then at the end of the day, you're going to have y equal to e raised to power x cubed plus c. This can be written as e raised to power x cubed multiplied by e raised to power c. Is that clear? So since c is a constant, e raised to power c is also going to be a constant. Abi? Yes. Alright, so I can just write this as saying y is equal to e raised to power, I'll say c. So you can have c there, you can have k, whatever. It's just a constant. E raised to power x to the power 3. Is that making sense? So that will give us the solution of that differential equation. So you should notice something now, that generally the variables will be separable if you can have differential equation in the form the y dx is equal to g of x multiplied by h of y. Does that make sense? That means you can separate out whatever you have on this side such that part of it will just carry only x and the part of it will carry only y. Does it make sense? So that's a variable separable or a separable differential equation. And whenever you have it, you can always separate them out and do a direct integration. Do you get it? Do you get that? Okay, so you can have it written this way where you have the y, the x, and you may have it such that you have the y alone and you have the x alone. You just observe if you are able to separate them out, then you are good to go. So give number 2 a try.
Yes, sir.
That's Roman figure 2. Number 5, Roman figure 2. Give it a try. You can see that these things are very, very cheap. Very, very, very cheap. It's just plenty. That's the issue. It's too plenty to put in a single course. Something you should have done like for 2 semesters. 7 days, 1 alone. It's too much. Hey! So have you been able to solve it? Where did you get to? Where did you get to your solution after your integration? Where now? What did you get after your integration? See, what did you get? Where now?
Square root of 4x minus 8 plus 2c over 3. Y is equals to square root of
Y equals to
square root of 4x
4x
minus 8
minus
8 plus 2c
plus 2c
over 3
over
3.
This is what you got? No. Okay. Alright, let's solve this together quickly. Let's solve it together. You have y prime is the same as y dx equal to x squared minus 4x plus 2 all over y, right? Okay, so is this separable? Yes. You can separate this out from this, and we can easily do that by cross multiplying, right? So when you cross multiply this, you are going to have 3y equal to x squared minus 4x plus 2x. Does that make sense? Alright, so when you integrate this now forget about this 3 in outside, then this spin outside, then you are going to have this to be what? 3y squared over 2, right? Equal to, what will this be? X cubed over 3 minus 4x squared, right?
Yeah.
Then plus 2x plus some constant. Then at the end of the day, multiply all through by 2, and divide all through by 3. So that's going to give us y squared equal to 2x cubed over 9. Does that make sense? Yes, plus 4x squared minus 4 squared. Okay, minus. Thank you. And this is going to give us what? Plus 4x over 3. Over 3. Plus 2 over 3. Yeah. That's still C. Don't worry about that. So, then you can take the square roots. Then this is going to give us y equal to plus or minus, square root of that here, 2x over 3 over 9 minus 4x squared over 3 plus 4x over 3 plus 3. Alright, so that's that. That clear? You can see that it's very, very short. Yes. Okay, like you do everything left to see outside. Yes. No, just do it this way. Okay. Are we good to go? So I need to attend all others. No. You can't solve everything now. You know one more. Okay, which of them? Number 7. Number 4. Okay, can we move on? Have you written this? No.
I didn't imagine the culture one.
Me now. 90 go sure now. You go see.
It's about applier.
Can we move on now? Okay.
Yeah.
Remember figure 4.
Zion.
Is it separate?
Zion. Zion the lion. When I think we do
Y prime, that's the Y. X. 4 is for Y minus X. Multiply by Z. Y. Then multiply by 1 plus X squared. Okay? So we're going to it's okay. This is the same as e raised to power y multiplied by e raised to power minus x, abi. Then multiply by z y multiplied by 1 plus x squared. Is that clear? So you can bring the variables together. E raised to power y, z y. Then multiply by e raised to power minus x into 1 plus x squared. Is that clear?
Why?
You are joining them. What's the issue? Why was?
Forgotten.
You love him now.
long gone.
Can we move on now? Can we move on? Okay. So this is the YDX. Then we can separate them out now. It's going to be 1 over e raised to power y, select y abi. Then the y, which is equal to e raised to power minus x into 1 plus x squared dx. Does that make sense? Yes, sir. So we are going to have the integral of this and the integral of this. So what will this give us?
An answer.
That's the answer.
Yes,
It's great.
It's only go finish now.
I don't get like this. So can you remember product to something like
UV minus
integral of u equal to minus integral of v. No, I got something like this before.
ó ti pẹ́ ọ̀tá àtijọ́.
Okay, let me tell you something. Hello, look at this.
Let me tell you something.
If you don't know, listen please. If you don't know integration, so you are very sure of your differentiation, and you are given a differential equation in an OBJ question, you know it's very easy. Just differentiate the options and see which of them will give you the differential equation.
Format.
So if you are given this kind of thing, you can look at the options, differentiate, each of them will satisfy the equation. The answer and move on. You get Hello, so we Let's see one after the other. Okay? The first one can be written as integral of cos y all over e raised to power y. Does that make sense?
Wait.
Set y is inverse of cos y. Can you remember that? I can also write it as e raised to power minus y, then cos y. Is it clear? Then I want to differentiate this with respect to, integrate with respect to y. Is that clear? So I'm going to take one of them as my u, together, and the other one as my v. So which one should we take as our u? Which one should we take as our v? How about? So I'm going to say that let u equal to, you can take either of them because both of them are easy to differentiate and also integrate. Together. Okay, so let's say u is equal to e raised to power minus y. So that's what? dv is equal to cos y dy. Is that clear? Do you understand this idea? Alright, so from here you can get your dy is going to be what? When you differentiate this, that will be minus e raised to power minus y. Does it make sense? Then when you integrate this, you're going to get your v is going to be equal to what? Sin y. Does it make sense? Alright, so that means that when you have du, you can replace du with du is equal to minus e raised to power minus y dy. Is that clear? So we can make all of these substitutions to this part. So let's do that. Okay. We can manage this way. So that's going to give us what? That means therefore integral of e raised to power minus y plus y dy equal to uv. So what is our u? Our u is what again? This. That will be e raised to power minus y multiplied by v. Our v is sin y. Then what else? Minus integral of v du. So what's our v now? Sin y. Then what's our du? Our du is this minus e raised to power minus y dy. So we have run into another problem. You can see that you have another product again. Right. So what will this give us? This is e raised to power minus y sin y, then plus